With Doubtnut, get instant video solutions to all your maths, physics, chemistry, and biology doubts. Just click the image of the question, crop the question, and get instant video solution. Download Doubtnut app today.
The question is, an LR circuit having a time constant of 50 milliseconds is connected with an ideal battery of EMF E. Find the time elapsed before the current reaches half its maximum value, the power dissipated in heat reaches its half maximum value, and the magnetic field energy stored in the circuit reaches half its maximum value. So this is our circuit. We have an LR circuit. This is our inductor and this is our resistor, and they have been connected to a battery of EMF E. Let's say current I flows through this circuit. So we know whenever there's a steady state current, what is steady state current? We can say constant charge flows per unit time. That means constant current is flowing through the circuit. And what would that constant current be? It would simply be EMF, that is voltage, divided by resistance of the circuit. So at steady state conditions, I naught, that is steady state value of current, is equal to E by R. Okay. Now this thing that is given to us, that is time constant. What is time constant? That is tau, right? Tau is given by L by R, inductance by resistance, and in this case we'd have that 50 milliseconds. That is equal to 0.05 seconds. That is our time constant. Now in the first part, we have to calculate the current that reaches half its maximum value. So the current reaches half its maximum value at steady state. So we can write, we have this equation for LR circuit. Current is given by I is equal to I naught 1 minus e to the power minus t by tau. This is our equation. Instead of I, we'll write half its maximum value, that is I naught by 2 I naught 1 minus, and instead of tau we can write 0.05 seconds minus t by 0.05, right? So if we take it here and this here, we can write it as e to the power minus t 0.05 is equal to 1 minus 1 by 2, that is 1 by 2. So we can write it as minus t by 0.05. Taking e here, it becomes log to the base e, log 1 minus log to the base e 2. Taking log here, it means 1 by 2, that is log 1 minus log e to the base e 2. Log 1 to the base e is 0 minus, this is 2.303 minus t 0.05. This and this cancel out. Our t comes out to be approximately 35 milliseconds. Okay, so this is our t in first case. Second is, the power dissipated in heat reaches its half maximum value. Now we're talking about power. Maximum power, this is A part, and B part is maximum power is given by I square R, right? I square R. Now we have to calculate the power dissipated in heat reaches its half maximum value. So half maximum value will be I square R by 2 is equal to I square R, right? Instead of I square, see, I square is equal to E by R, I square is equal to E square by R square, and then one R and R go, so we're left with E square by R. So we can write it as E square by R to R is equal to E square by R. But we have thing here, like instead of I, we can replace this with this equation. So we'll get 1 minus e to the power minus t by tau, that is tau is L by R. So if it's in the denominator, we'll write R by L, okay, whole squared. See, we're just squaring the current. Okay, so after this and this, they cancel out and they also cancel out. This square comes here and becomes 1 by root 2 is equal to 1 minus e to the power minus t by t into R by L. Okay, after this we can write it as e to the power minus t r by L is equal to 1 minus 1 by root 2. That is root 2 minus 1 by root 2. Okay. After this, we can take it here and it becomes log. And if we solve this thing, it is e to the power minus t r by L is equal to root 2 by root 2 minus 1, that is 1.14 minus 1 divided by 1.14. Okay, after this we can write it as t is equal to, this thing is 50 into this thing becomes 1.2275. okay, and after this t is equal to 61.2 milliseconds. Actually under root 2 is 1.41, not 1.14. okay, and then how we got this 50? We got it from r by L is 1 by 50, and when we take e here it becomes log. So we can write minus t by 50 is equal to log of this, and that is equivalent to 1.2275. So we have t by 50 here, so 50 comes here, 50 into 1.2275 is equal to 61.2 milliseconds. That completes our B part. C part is the magnetic field energy stored in the circuit reaches half its maximum value. So we need to calculate the magnetic field energy. So current in the coil, I stated earlier, was that I naught, that is steady state value, is equal to E by R, right? And magnetic field energy stored at steady state is that U, we represent it by U, is given by 1/2 of Li squared. Okay, and instead of I squared we can write 1/2 of Le square by R square, right? And after this we need to calculate, it reaches half its half is 1 by 4th, so we can write 1/4 Le square by R square is equal to 1/2 of Le squared by R squared. And like we did in that question, we have 1 minus E dr by L whole squared. Okay, so they cancel out, 2 1 2 2. Okay, so we have here 1 by 2 is equal to 1 minus e to the power minus, let's write t by 50 here, okay, because r by L is 1 by 50, right? So this implies 1 by root 2 is equal to 1 minus e to the power minus t by 50. Okay, after this we can write it as 1 by root 2 is 0.07, that is equal to 1 minus e to the power minus t by 50, and then subtracting it, this implies e to the power minus t by 50 is equal to 1 minus 0.07, and then if we take this in the denominator, or let's say simply write a log of 1, and then we can do it, minus t by 50 is equal to log of 1 minus log of, that is minus log of to the base e 0.07. So we eventually reach to this result, that is t is equal to 50 into log to the base e of 0.07, and then we get value that is 61 milliseconds. So that completes our third part. Thank you.
For class 6 to 12, IIT JEE and NEET level. Trusted by more than 5 crore students. Download Doubtnut app today.